Welcome back. This is Mr. Hassan's Maths channel, and I'm now answering question number 10 from the P1 endotopic worksheet number 8 integration, which is basically from the CAIE syllabus, the Cambridge syllabus from 9709. But this is a question that I have modified from some other places. It's not actually a Cambridge question, it's from some other examining board, and I have kind of changed it a bit to be able to apply some kind of type of questions which are newish in their style. Okay, they're not really new in their content, but in their style in the Cambridge syllabus. I don't want to use the questions from the past papers which are similar to this to allow the students to basically practice those questions from the past papers later on. So I've chosen something which I modified to make it similar to those. So anyway, what we have to do here is, first of all, we're given this diagram. It shows the curve y equals 4 over x, which is this curve here. So this is the curve y equals 4 over x. The shaded region R, which is this one below the curve, is bounded by the curve, the x-axis, the lines x equals 2 and x equals 6. But the shaded region S, which is above the curve, is bounded by the curve, the line AC and the line BC. Okay, the line AC, which are straight lines. This is a vertical line, this is a horizontal line. Now, what we've got to do here is find the volume of revolution of the solid produced when. Now, first of all, we're asked to do that when the shaded region is S is rotated 360 degrees about the x-axis. So this region S, which is the part above the line and bounded by these lines here, has to be rotated 360 degrees about the x-axis. About the x-axis. Okay, so what I've got over here is I've just got rid of the part that says R, so it's a bit clearer for us. Okay, so we're finding the volume formed when this region is rotated around the x-axis. Now, what we're used to having, and the reason why I've chosen this particular question to do, we're actually used to having questions where you've got like a curve and you're rotating, you've got the area between the curve and the x-axis, and you have to rotate that area 360 degrees about the x-axis, and you end up with a series of cylinders, okay, which you have to find the volume of by integrating this function between the points A and B, okay, and you take the function, and as we know, the volume is pi times y squared dx, and the reason for it being pi y squared pi times y squared dx is because we consider a small cylinder in this area, in this section here, and if we take that cylinder, okay, it has like a radius, which would be this length here, which will be basically the y coordinate of the point here. Okay, that's the radius of the cylinder, and the vertical height of the cylinder, the height of the cylinder, the thickness of the cylinder is a small amount on the x-axis, very thin cylinder, which we call dx. So we know the volume of a cylinder is pi r squared h. In this case, r is y, and h is dx. So the volume of this small cylinder is going to be pi times y squared dx. And if you want to find the sum of all of the volumes of all the cylinders between A and B, then we can integrate this between the points A and B, and that gives us the volume of all of the cylinders between those points. So that formula y, pi y squared dx, comes from, okay, the volume of a cylinder, and it's basically the sum of all the cylinder formed, okay, between the two limits that we have to revolve this area around the x-axis. Because when you revolve it around the x-axis, you end up with a three-dimensional shape. Okay, it's like a solid revolution. So now, what we have here, though, is something slightly different, because it's not all the way down to the x-axis that we're considering the area. We're considering the area, which is like, this section over here, you could say. So just imagine you take a small strip in this section over here, just one small rectangular strip, and you were to revolve that strip around the x-axis. Okay, if you were looking from this direction over here, you would end up seeing something that looks like this. Be like a donut type of shape. Okay, because it'll only be that part that rotates around. So that comes all the way around the x-axis. Okay. And you will have like a donut shape in the middle. Like in the middle, there'll be a gap. That gap there will be a gap underneath as well. It's a bit difficult to envisage this, but just it's like it's coming out of the page. Oops, what did I do there? Got rid of all those bits I didn't want to get rid of. So it's a bit difficult to envisage. It's like the whole thing is coming outside of the page. It's like it's coming outside of the page and wrapping around the x-axis, going back inside the page. Okay, but you see, it's only going to be that part. It's just that part. You see, that's the part that's going to come out of the page, and it has a small little thickness. So you basically, if you can imagine that, looking at that on the side, you will end up with something that looks like this. Okay, if you're looking at it like along the x-axis, you'll see something like this. There will be a hole in the middle, but that will be a solid, and it will have a thickness that's going down into the page. Right, so what do we do to find the volume of this? Well, what we can do here is we can say, okay, it's like it's got an outer volume, an outer radius, and an inner radius. To find the area of the cross section of this kind of, cylinder with a hole in it, you're going to use pi times the big radius squared minus pi times the small radius squared. Okay, so that would correspond to here. The big radius would correspond to, in this diagram, it would correspond to this length from there to there, the outer radius. Okay, so it's like the y value of the point up here. That's what it would correspond to. The y value of the point up here, which is going to be the y value along this line over here. Now we have the curve y equals 4 over x. So this line is when it meets there when x equals 2. It meets this line when x equals 2. So when x equals 2, y equals 4 over 2, which is 2. So when x equals 2, y equals 4 over 2, so y equals 2. So this is the line, y equals 2. So we can see here that, the distance between there and there is 2. But the distance between there and there is whatever y coordinate this curve has at that point. Okay, so what we can do is we can think of this as basically, let's call this line, we know it's y equals 2, but let's call it y1, and let's call this y2. So basically, the area of this cross section would be given by pi times, you can say y1 squared minus pi times y2 squared. That would be the area of the cross section. Okay, and then that has to be multiplied by how thick this cylinder is for the volume, which we're going to call a small amount in the x dx. So what we can say here is the volume is going to be given by, we can say take the pi out, and we can say if we integrate between the two limits that we need to find the volume, between 2 and 6, pi times y1 squared minus y2 squared, taking pi as common, and dx. So it's like the outer radius squared minus inner radius squared times pi is like the area of this cross section multiplied by dx, which is the volume of this little cylinder. Integrated between 2 and 6 means you add together all of those volumes together. So this is a formula that will help us in this type of situation. Okay, there's also another way to do this, which I'm going to show you as well, but I like to write the pi outside eventually. So this is one formula that will help you to find the volume of revolution when something is rotated around the x-axis, but it's not the whole thing. It's like two functions, the area between two separate functions being rotated around the x-axis. So you take the higher function, the one that's higher up, okay, first, and you square that function, take away from it the lower function squared, and you subtract them, and then integrate that with respect to x between the limits given, multiply everything by pi, and that will give you the volume of revolution of the shape that's formed when this S is revolved around the x-axis. Okay, so that's what we're going to do now. So we know that the y1 is basically 2. So y1 is the line y equals 2, and y2 is the function they gave us, 4 over x. So I just have to put these in here, and hopefully that will give us our answer. So you have pi times, we have 6 over 2, so you're going to have y1, that's going to be 2 squared, which is 4 minus 16 over x to the power of minus x squared, sorry, and integrated that with respect to x. So let's see what that gives us. Pi times, let's get this ready first. We haven't got it ready. 14 minus 16 x to the power of minus 2 with respect to x between 6 and 2. So now that is ready to be integrated. When we integrate this, we get pi. We don't need to write the integral sign once we started integrating. Okay, so we can just say square bracket. Don't forget the pi. Don't forget the pi. It's very easy to forget about the pi. Common mistake. That's equal to pi times, and you have 4. When you integrate 4, you get 4x. You integrate minus 16x to the power of minus half. You add 1 to the power. That gives you 16x to the power of minus 1. So you have minus 16x to the power of minus 1 divided by the new power, which is minus 1. Okay, so I'm just writing the working here as well. And that's the limit 6 and 2. And that will give us pi times. And now let's get this ready for substituting things in. That's 4x. And that's a minus, and minus gives you plus. You'll have 16 over x. Now, hopefully, this will give us the right answer. So we have pi. And now we're going to put the values of 6. So 4 times 6 plus 16 over 6 minus, and then you're going to have 2 times 4, that's 8, minus 16 over 2, that's another 8. Okay, plus 16 over 2, that's another 8. So we're almost done now. So you have pi. We got 24 minus 8 over 3. And you're going to have minus, that's 8 plus 8, which is 16. So we end up with 24 minus 16, which is 8 minus 8 over 3. Sorry, plus 8 over 3. There's a plus there, sorry. So that's going to be 24 minus 6, that's 8 plus 8 over 3 times pi. So that's going to be 16 over 3. No, it's 24 over 3 plus 8 over 3. 24 plus 8 is 32 over 3 pi cubed units. Or units cubed if you want. Okay, so I guess I'll write it as units cubed. That's better. Okay, so whatever units it is going to be cubed. Okay, because it's a volume we found. Okay, so that's a bit long-winded, but I just wanted to give you an example of a type of question that could come up and has come up, but not with an actual question from the past papers, because I want you to practice them, all right, from there and have more exposure to these type of questions. It's not easy to find questions like this, but, you know, it's becoming more common. So now, as I said, there's another way of also dealing with this question, and that would be if we did kind of the opposite. If we found the area of this, or we found the volume of S of the whole cylinder, like if you revolve the whole thing around, you'd have like a whole cylinder from AC, because it's just a horizontal line. So we could find the volume of the whole cylinder, which would basically be, if you think about it, that's your radius, which is from 2 to 2. So from 0 to 2, which is 2. That's your vertical height, from 2 to 6, which is 4. So the volume would be pi times r squared times height, h, which would be pi times 2 squared, which is 4, times the height, which is 4. So you end up with 16 pi. Okay, that would be the volume of this big cylinder. And what we could do is we could take away, if you want to find the volume of S, and when it's revolved round, we could take the volume of R as it is revolved around this x-axis, okay, and we could work out what that is. And we know that the volume of R, of this R shaded region R, when it goes around, is going to be basically pi times y squared dx. In this case, y is just simply 4 over x. So we can just do pi times 16 over x squared with respect to x between 2 and 6. So you have pi times 16 integral of 16x to the power of minus 2 with respect to x between 6 and 2, which will give us, that will be 16x to the power of minus 1 over minus 1. Pi limits 6 and 2. Now, when we substitute the values in, you'll end up with pi, and you're going to have minus 16 over x. 6 and 2. When we put those values in, you'll have pi times minus 16 over 6, which is 8 over 3. That's minus 8 over 3 minus, and you're going to have, when you put 2 in here, it'll be minus 16 over 2, which is minus 8. So you end up with, basically here, that'll be 8 minus 8 over 3. Now, 8 is the same as 8 over 3 is 20, so that will be 24 over 3. So minus 8 over 3 plus 24 over 3, and that's multiplied by pi. So minus inside there. 24 minus 8 is 16. So that gives you 16 pi over 3. 16 pi over 3 is the volume of this section here when you rotate it around the x-axis. Now we need to take that away from the volume of the whole cylinder, because it's like we're finding the volume of S when it's rotated around, and this is like a blank space here. So if we subtract this from what we found in the beginning, which was that the volume was 16 pi of the whole cylinder, so we're going to have 16 pi minus 16 pi over 3, which is 48 pi over 3 minus 16 pi over 3, which gives us 32 pi over 3, which is exactly what we found. 32 pi over 3. Yeah, so that's an alternative way of getting the answer for 10 part A. Okay, where we take the volume of this whole cylinder, okay, which is the cylinder that's formed when AC is rotated, the whole thing from this whole rectangle, R and S together, rotated around the x-axis. Take away from that the volume of this part R rotated around the x-axis, and then subtract those two volumes. You ended with what's left, S, which is what we need. We want the volume of S when it's rotated around the x-axis. Okay, so there's part A of that question. All right, two kind of different ways of doing it. Now I'm going to go on to part B. Now part B is where we have to find the shaded region R rotated 360 degrees about the y-axis this time. So in this case, we're not really concerned about the S part. We're concerned about the R part. This part has to be rotated around, but not the x-axis this time. Now it's rotated around the y-axis. So it's rotated around the y-axis like this. So this stops there. So it's gonna go like this. It's gonna stop there, and the whole thing is like gonna be some sort of volume that looks something like this. Okay, I'm just trying to. It's not very well drawn because it's gone too far there. It's supposed to be a bit more. Let me just correct that, because that's right in the middle there, the y-axis. Okay, make it a bit more realistic looking. Okay, so it's going to look something like this. Okay, something like this. Something like that. Yeah. So it's rotate this region R around the x-axis. Now this is going to have like this hole in the middle. Okay, it's going to have this hole right in the middle, which will be like the cylinder formed over here. Okay, so this is what we can understand. So in this case, when you're revolving around the y-axis, then the cylinders, the small cylinders that are formed from those areas are like this. And if we were to consider the area all the way to the y-axis, then we would have like a cylinder that's solid. And this would not be the y value now, this would be like the x value. This is like the x values. Okay, and this would not be a small amount of x, it would be a small amount of y, so we call it dy. So the volume of this now is going to be pi times the radius squared, which is x squared, times dy. So if I want to find the volume, okay, of this shape, then I've got to go all the way from, wherever we want to start to wherever we want to end. So we can put between A and B, and that will give us the volume of something revolving around the y-axis this time. Pi x squared dy. So when it's around the x-axis, as we saw in part A, the volume is pi times y squared dx. But when you have to revolve it around the x-axis, if that's where you have to find the volume of revolution around, then the volume would be pi times x squared dy. That's the difference between those two. All right, so now, how do I relate that to this shape here? And let me just tidy this up a bit so we can figure out what to do here. Now, the problem in this question here is you've got like two separate sections. Okay, so we can again do this in two different ways, but I'm going to choose one way here, where I'm going to consider this as two sections here, because you've got this curved part, AB, and then you've got this straight line part. If you're considering revolving around the y-axis, okay, then you've got like this curved part, which is y equals 4 over x, and then you've got this straight line part here, and then you've also got this straight line part here where, you know, you have to stop. You don't want to find the volume of that. Okay, so what we could do is we can consider this as two separate shapes. Okay, we can consider this as two separate shapes. That would make life a bit easy for us. So I can consider the top part here and the bottom part here. The bottom part here is pretty easy to find. It's like the volume of a cylinder of, well, a cylinder with a hole in it. Okay, so you have like the outer radius is 6 and the inner radius is 2. Okay, so as we said, the volume of a cylinder like that would be pi times r squared minus small r squared times h. So the small radius here would be, you'd have the big radius would be 6, so you have 6 squared minus 2 squared times h, and h would be how high the cylinder is. In this case, if you were to revolve it around this would be the height of the cylinder. So we've got to find out here. We know y equals 4 over x. So this point here is 2 over 3. Okay, and this point here is 2. So when x equals 2, y equals 2. When x equals 6, y equals 2/3. So the height of this cylinder here is going to be 2/3. Okay, so that's going to give me the volume of this part when it's revolved around the x-axis, this part of this region R, and then I'll have the rest of it to deal with it later. That's going to be pi times, that's 36 minus 4, which is 32, times 2 over 3. So the volume is going to be 64 over 3 pi units cubed. That's this bottom part. That's the cylinder form from the bottom part. Then I've got to think about the shape form from the top part here between 2/3 and 2. Now in this case, we have to consider that we have to have our equations in terms of x, not in terms of y this time. So we have y equals 4 over x, which is the same as saying x equals 4 over y. So, and we've got to consider again, there's a hole here. So again, we've got to think about, if I consider a small section from here, it's going to have an inner radius here, which is in this case 2, but I will call it x2. It means like the second function. And then you have the outer radius, which would be from there to there, which would be, this would be x1. This would be the x coordinate of this point here. And if you want to find the volume and there's a hole in the middle, then we've got to think about x1 and x2 and subtracting them. So you're going to have the volume when you have this kind of situation is pi. And you're going to have the outer radius x1 squared minus the inner radius, which is x2 squared. That will be the volume, that will be the area of the cross section times how high it is, which is dy. And that will give you the formula for when there's like a gap, where there's a gap between where the curves end and the axis around which you want to find the volume of revolution. So now our x1 in this case is 4 over x. That's the one that's the outer radius. And our inner radius x2 is going to be the line x equals 2. X equals 2, right? So this is going to be 4 over y, sorry, not 4 over x, 4 over y. Why? Because we're making x the subject. So this is x1 equals 4 over y. Okay, that's the equation of this curve when you make x the subject. So now what we're going to do is we're going to say v equals pi times the integral between the limits a and b. In this case, the limits are between 2/3 and 2 of, and you're going to have x1 squared, which is 4 over y squared minus x2 squared, which is 2 squared. And you're going to have this integrated with respect to y this time. Okay, so now we're going to have the volume equals pi times 2/3 2, and this is going to be 16 over y squared minus 4 dy. So that will give us pi times Now we can start to integrate. Let's just rewrite this as 16y to the power of minus 2 minus 4 dy. Now we can integrate. When we integrate this, get rid of the integral sign now. We got pi, don't forget the pi. Always don't forget the pi. It's very easy to forget it. So that's equal to pi times, you add 1 to the power, divide by the new power. You'll end up with 16y to the power of minus 1 over minus 1. So you have negative 16 over y, basically. Minus 4, the constant term gains is the y because we're integrating with respect to y. And then we have our limits of 2/3 and 2. So now we're ready to substitute the values in. So you have pi times, you have minus 16 over 2, which is minus 8, minus 4 times 2, which is also minus 8, minus, and then you're going to have 2/3, minus 16 over 2/3. That's like 16 times 3 over 2, which is 24. Okay, if you divide 16 by 2/3, you're multiplying it by 3 over 2. 16 divided by 2 is 8. 8 3s are 24, so it's minus 24. You're going to have minus 4 times 2/3, which is minus 8 over 3. Okay, so we're almost there. So you have pi times minus 16, minus, that's going to be minus, that's a minus here, so it'll be plus 24 and plus 8 over 3. Sorry about that, because that's a minus and that's also a minus. Okay, so that's plus 24, so that's 24 minus 16, which is 8. So you end up with pi times 8 plus 8 over 3. That's 24 over 3 plus 8 over 3, which is equal to 32 over 3 pi. And that is the answer for this question. Units cubed. Okay, so that's one way of getting the answer to this question. We end up with 32 over 3 pi square or cubed units. Okay, sorry, that's not the end, of course. That's the volume of just that section. We haven't finished yet. Don't get too excited, right? That's the volume of that section, which we have labeled as part 1. After we rotate it around, that's the volume of part 1. So the total volume is going to be the volume of 1 plus the volume of 2. And the volume of 2 we found earlier as being this. This is the volume of 2. Okay, which is 64 over 3 pi units cubed. So we're going to have 64 over 3 pi plus 32 over 3 pi, which gives us, that's 96 over 3 pi, which gives us what? 3 goes into, yes, that's 32 pi units cubed. And there's the answer, 32 pi cubic units. That's the total volume after all of that work of this whole section here. Okay, when you rotate it around the y-axis. Okay, so that's one way of dealing with this question. Okay, and yeah, because we've got to find the volume, all of the shaded region, including that bit. If it was just this bit above the line here, then all we'd have to do is this, of course, just this part here. But we have to also find the volume of this section below that line. So all that shaded region are. So I considered that as one cylinder, and I found the area, the volume of that cylinder, and then I considered the volume if you rotate this small section around the y-axis. Okay, it makes it like a disc shape with a hole in the middle. So we need the outer and inner radius, which is the outer and inner, graphs in terms of x equals 4 over y and x equals 2, and you have to square them and subtract them from each other. That gives you like the cross-sectional area, basically. Multiply that by the height, that gives you the volume. So we have to find the volume for all of those little discs between 2/3 and 2, and then add the cylinder at the bottom, and we get our answer, 32 pi cubic units. So that concludes question number 10, A and B. It's a bit like long-winded, and I don't think you'll find that many questions like this, but it's possible for them to give you a question like this, so it's good for us to know how to deal with it. And that's why I chose this question, and I in fact modified the equation in such a way that you would be able to solve it, because many of these questions, volumes of revolution, in the other examining boards come in P3, P4, where you have to apply it to situations involving types of integrations that we don't cover yet in P1 in Cambridge. So that's why I had to modify a bit. Anyway, I hope that was clear. And, as I said, there's no paper that this is particularly from. I found this question in, I think, one of the other papers, and I modified it. So it's not really actually the question that was asked in the paper. Question, I think, the answer in the paper was about areas. I made it into a question about volumes to practice this technique or these techniques. So I hope those, explanations were clear. I hope you understood. Um, if you want to see other questions from this particular worksheet on integration, my end of topic worksheet number 8, you will find the playlist for that over here in this region. Other questions from integration of P1 from Cambridge can be found in the playlist in this region over here. You can subscribe to my channel by clicking on this link, and you can find other videos that relate to A-level or IGCSE work. You can find out how to use my channel by watching the video that will appear linked over there. Thank you for watching, and see you soon.